I checked the recording and the mic was fine in the recording. If I make it louder for the live stream, my fear is that it will get noise in the recording. So I prefer to keep it a bit low. And if you're watching from home, you just crank up the volume a bit. Right, before we start, a little question, just so for those of you who've had some theoretical computer science in undergrad, that's one of the things that you usually cover there. Now, we don't actually need this. This is more kind of a proxy question to remind you of the things that are often covered in these lectures. Of course. There are two different formalisms. I mean, this would be the topic of like a week or two each. So regular expressions are what you usually know from programming, right? Regexes are, people like to distinguish regular expressions, which is the formal language version, which just can do A or B, or it can do A star, and that's pretty much it, and concatenation. Whereas regular regexes, as you know them from programming, they're often expanded with additional features. But that's the one thing. Regular grammars are, you know, context-free grammars? So a regular grammar is like a context-free grammar, but you can only have the non-terminal on one side. Always on the left or always on the right. Yeah. Maybe they're also called linear grammars sometimes. Again, this is all kind of not super relevant for this module. I thought it's a good proxy question because it's two different questions. Do you remember having seen a module of the title Theoretical Computer Science some years ago? Or do you remember what you covered there? Here's what you voted. And I mean, these are all just for fun. They're anonymous, so don't feel obliged to correct your answer now. There's no point in doing that. This is just for your information or for our information and for a bit of fun. You could put in several answers. That's why the percentages don't sum up to 1, obviously. That confused me for a second. It's still big enough to read, right? As I said, not really relevant for the module. But yeah. Right, so regular grammars are a subset of context-free grammars. No, it says the same languages, right? So they accept all of the regular languages, but more. The formal argument would be the pumping lemma, but we're really digressing into a different module that we shouldn't. Let's see, I have another one that's more on topic. And with this, I'd like to come back to our the topic for today. Combinatorial optimization problems and decision problems and all that. So again, if you've done some theoretical computer science undergrad module, this is likely a problem that you've looked at, although can't say for sure. It's one of the more well-known, and so you can use this as a little test whether you remember these things. By the end of today, you should be able to answer this anyways, but let's do a little pre-check. And while you still vote, let me recap briefly where we left off yesterday so that we're on the same page for all of the following. I gave a rough overview about what this theory of NP and NP completeness is about. I won't repeat that part. And then I said, if you want to make statements like the impossibility results that stem from NP completeness, which are, there is no algorithm that can solve this problem in polynomial time, which again, we can't formally prove, but we can make some statements like, at least if there's this problem is at least as hard as some others. All of these statements need a way to speak about all allowable algorithms. So you need to formalize what an algorithm is. And for that, we need a formal model of what computation is, or what a machine is, a computer is. So the first model I presented was this random access model, which is the gold standard if you want to have precise statements about computational complexity and the cost in a CPU. But it's fairly detailed and is very low level, and it gets tricky to work with. So instead, I want to give a very short run through of the historically first model, and the one that's often at the basis of complexity theory, just because it's well suited for that. It doesn't really model any actual machine. That's not its purpose, or has never been its purpose. There's more than 11 people in the room. Is someone still thinking about this, or shall we reveal what you voted, or what the 11 people voted? Three, two, one. So there's the votes, and if you can see all of them. Yeah, most was right, so you could have selected most answers. It is an optimization problem. We'll define it later. We don't know whether it's in P, to be fair, but likely not. It is in NP, and it's NP hard, and it's NP complete. We call the problem tractable if it's in P, meaning it has a polynomial time algorithm. We'll come back to all of this, but yeah, and it is algorithmically solvable for sure if you don't care about the running time. Yeah. I just threw in this last answer because there are problems that are not even algorithmically solvable, irrespective of the time you give a machine. In the next section, we'll look at Turing machines. After studying the word RAM model for a bit and finding that it is a little too detailed and complex, let's go back to a model that's really designed to be as simple as possible. We talked about this yesterday already a bit. There's many more models of computation that you could study. And indeed, a theoretical computer science course often spends a third or so on studying different formalisms of what computation can be, and then proving that they're all equivalent in the sense that they compute the same set of functions. So there are these famous undecidable or uncomputable problems, like the halting problem, which are not effectively computable with any of those formalisms. But apart from those, all the functions that are computable on any of these models are computable on all of the other models too. And the list you can make much bigger. There's fun things like the game of life happens to be Turing complete. Cellular automata as a general concept, if you pick an interesting one, are Turing complete. So all of these, any programming language that is interesting will be Turing complete, and so is not just able to express all of these models, but the other direction too. They can all simulate each other. And there's the Church-Turing thesis that says whatever model you come up with, as long as it formalizes something that means effectively computable, it'll be equivalent to those in terms of the functions that they compute. Now, this is not provable because it's not clear how to formally grasp all possible ways to define this. So it's just a kind of working hypothesis, but it hasn't been falsified. And there's an extended version of this that takes running time into account. Many of these models have very strange and different notions of time. We'll look at the one for Turing machines. You've seen the one for the word RAM. I didn't even bother to list that, but it's kind of a register machine. Cool, not on the list. But of course, word RAM is one of those. In a cellular automata, time is a very different thing because many things happen in parallel. Despite all of that, if you look at the models that we have, they can simulate each other with polynomial overhead. Again, I leave this vague for now. The extended Church-Turing thesis is that whatever model you can come up with, it'll be able to simulate all the others with polynomial overhead and vice versa. That's a stronger statement. And indeed, it's not clear if this is true for quantum computers. So for all the other models, I think is clear or proven to a degree. For quantum computers, I think this is unclear. And also, what I'm saying here is about theoretical models for quantum computers. None of the existing ones is really exciting. If you look at what they actually can solve in terms of practical problems, well, different story. But they might be the exception to this extended Church-Turing thesis. What we'll look at is the historically oldest and simplest of these models. I love this. The paper was received in May 36 and read November 36. I suppose this means published. And in between, there was a bit of peer review and typesetting and so on. So this is Alan Turing's paper where he introduced Turing machines and also showed that this halting problem, that's the German phrase that was used at the time because Kurt Gödel coined the term and so on. But I really have to cut the history lesson short. What Alan Turing set out to do was formalize what you can do with pen and paper and as a person computing things step by step. He really thought about the algorithms you learn in primary school for doing arithmetic. That's what he had in mind. And he thought, how can I possibly generalize this to the biggest extent? That's what he came up with. And well, some geeks build a physical version, which is not by any means the most reasonable way to build an actual computer, but it's possible. Okay. And of course, they're also in wide circulation. I've spent until last summer, I spent 5 years in Britain. So this is a picture I took of an actual note with Alan Turing on it, and he invented some shorthand for his Turing machines. That's what's on the bill. Otherwise, it's a bit hard to decipher. But yeah, they're very proud of Alan Turing, and for a good reason. Informally, very briefly, what is a Turing machine? It has this conceptually infinite tape, like in this picture. You can extend it on both ends as much as you need. It has a single position that it can look at, and it reads one symbol there. And then it has a finite control, which contains a finite number of different states. This is a piece of memory, working memory, if you want. And these states encode the whole memory of the Turing machine outside of the tape. And in each time step, it reads one symbol and it is in a certain state. That tells you where you are in this table. And then the right-hand side tells you what to do, which is write a different symbol at this cell on the tape, move your read-write head one position or stay, and go to a new state. And that's all you can do. There's a special state where you terminate the computation, and that's it. So it's very restricted, and it's at first not clear why this would be powerful enough to do all computation imaginable. But it turns out it is, and it's the same expressive power as any programming language. The goal of this part, though, is to formally define this, make it a bit more rigorous. So for that, a Turing machine is really a collection of all these pieces of information. It's a finite set of states, that's capital Q. It's an input alphabet, that's the alphabet, the symbols that you can write your input onto the tape initially. There's a tape alphabet, which is a bit bigger, so it contains the input alphabet, but it might have additional symbols that you allow the machine to write on the tape for temporary storage. Then there's a transition function, and there's two cases. The normal way computers work would really be a deterministic Turing machine, where the transition function, like in the example here, is unambiguous. If you're in a certain position, combination of a current state and a tape symbol that you currently read, there's a single thing you do, and that's given by this function delta. It maps from the states that are not the halting state and the current tape symbol to a new state, a new symbol that you write, and a movement of the read-write head. But we'll also need non-deterministic Turing machines, which are really strange beasts. They're not intuitive, they're not physically producible, but they're sensible to define, and you'll see why soon, if you don't know already. In this case, we also have a function that maps from a current state and a tape symbol to something, but now that something is a whole set of possible next states. And the computation will have to somehow know which one to pick. The other pieces we need is some initial states so that we know what's the state called where we start. We need a blank symbol, so the tape is initially filled, and because it's infinite, we don't want to do this explicitly, so we just assume it's filled with these blank symbols initially. That's part of the tape's alphabet. And we have a special state that means if you ever reach this state, then the computation stops. What I defined here is basically just the syntax in logic speak. I'm just defining in set theoretic notation certain things. I've already given you the meaning behind them, but technically that's separate. And defining the meaning a bit more rigorously will take 1 or 2 slides. We've already talked about the steps of computation. If I'm in a current state and I read a current symbol, then this transition function or transition relation tells me what the new state is, what symbol I write on the tape, and where I move the head. And here's the semantics spelled out. I essentially verbalized that on the previous slide. Sometimes it's useful to distinguish between the syntax, which is what can you write down, but these are just empty symbols with no meaning, and the semantics, which is what's the meaning behind it. And I tried to separate this here a little bit. Again, the important part to keep in mind, a deterministic Turing machine has a uniquely determined next action, whereas a non-deterministic Turing machine may have several ones. And for now, this is just a definition. It tells you there's several things you could possibly do, and it doesn't tell you which one to actually execute. Now, the memory of the Turing machine is just the state, as I said, but the state of the world includes this infinite tape. So if we want to specify the full computation, we'll also have to capture what's on the tape. And that's done with the notion of a configuration. Configuration is kind of a snapshot of the entire world as seen from the eyes of a Turing machine. And we write this as one long string, which is just a shorthand. There's a string, so this star means 0 or an arbitrary number of occurrences of letters from this alphabet. So gamma star means as many tape symbols as you like, followed by one state, followed by potentially more tape symbols. So each configuration will have this form alpha q gamma, where q is a state, and then alpha beta together, that should be gamma, I guess. Or rather, the first one should be beta. So these two together are the entire tape content, read from left to right. And they're separated so that you can say where the read-write head is. So it's kind of very concise notation. This position of the state tells you the first symbol of beta is where the read-write head sits currently. Other than that, it's just a very concise way to capture the whole state of the system. And then we can define what a computation looks like. It's a relation between configurations. The computation tells you you're currently in one world, then you can do one computational step, and that transforms the world into a slightly different world. Most of the tape will not be modified. As you see here, these A's remain unchanged. In the first case, where you don't move the read-write head, don't move. Then you just replace this first symbol of B, of beta, with a new symbol C given in the transition function. And you go to a new state, Q prime instead of Q. And the other two cases are similar. You just have to model that the read-write head moves. If you move to the right, it means this symbol that you wrote is then on the left of the read-write head. So you basically swap those two. The rest is the same. Whereas if you move to the left, you have this symbol here that you wrote, and then you move once to the left. So you're sitting on this symbol now. So you have to move Q prime one position left. OK? It's nothing really deep, but I want you to get a little into touch with formal notations, just because they make it possible to be super rigorous about things. There's two cases that are not captured by this general case, which is just the boundary cases. If you're at the end of the tape content that you specified, we imagine the tape to be infinite, but it is filled with these blank symbols. So no need to write infinitely many blank symbols left and right. We don't do that. Instead, we just fill up with new blank symbols as needed when we move further left or further right than we've previously been. And that's what these two cases capture. If you're at the end of the encoded tape symbol and you move further to the right, then you just add a new tape blank symbol. And the same on the left. If you're currently sitting on the leftmost symbol that you've explicitly captured, then you add another blank symbol if you further move left. Okay? This way, a configuration is always finite, at least if it has been running for finite time. The Turing machine cannot have done more damage to the tape than change a finite number of symbols. But it is conceptually infinite. You can make more space as you need it whenever you reach the boundary. OK. Good. That's configurations and the computation relation. Relation here just means there's pairs of configurations that you put in relation so that you can go from here to here in one step. It's not a function that you go from here always to this one, because we have these non-deterministic machines. They mean there's several possible next steps. Here's an example from the one before where I just spelled out the configuration. You can just read this up for yourself. And just what I said before, this entirely captures the state of the world for the Turing machine. There's nothing else that's ever relevant for the computation that wouldn't be in the configuration. OK. Now we know how these Turing machines work. Now we want them to do something useful. So we want the outside API of a Turing machine. And that's the function that's computed by it. So we're given some Turing machine. Again, this lovely 7-tuple, just as a convenient shorthand to write this down. Now this machine M, when I give it an input X, what that means is I initially write this input on the tape and nothing else. And so I can define what this function is now in a very convenient and short way. The function is all possible strings y that I can reach if I start in the starting state of the machine with x on the tape and nothing else. And I can, with an arbitrarily long sequence of steps, so the star again means the transitive reflexive closure in fancy speak, but really an arbitrary number of executions or iterations of this relation. I can reach from this the halting state with y to the right. So implicitly, I'm telling you here how we're supposed to use Turing machines. Put the input on the tape, put the read-write head on the first symbol of the input, let it run, and you want it to reach the halting state and be at the beginning of the output. If it does anything else, if it stops and is in the middle of the output, we're not formally allowing this. This is kind of an illegal behavior, okay? So we're a bit strict maybe, but it's convenient to define it that way, and you can always modify your machine to move back to the beginning if that's what you want. This definition works for both deterministic and non-deterministic machines. For deterministic ones, we'll always have a single element in this set because every step is clearly defined. You can only go in one way. It's less or equal 1 because if you screw up the programming of the machine, it might never reach the halting state. And then there's maybe no such y so that it reaches a halting state. You've programmed an infinite loop, right? We've all done it before. If that's the case, if we have a deterministic machine, we'll just write it as a function and be a bit sloppy with the set notation. If we know that there's a single element in the set, we'll just write it like that. For a non-deterministic machine, it could be that there's several computations and they produce different outputs. For now, we'll accept that. Okay. Now we know how a Turing machine can compute a function. Now we need to talk about the cost of that. And we can define time and space in this world of configurations as well. Time is kind of easy. It's this is the important bit. Would have wanted to do that in red maybe. So it just says the time that the machine takes on this input x is essentially how many computational steps it needs to reach the halting state. Now there's a catch. There's an infimum around this because it could be a non-deterministic machine that has several computations. Then we take the longest running one. And we also include if you somehow mess up and it doesn't ever reach a halting state or is even completely broken, then maybe you need this catch-all case of going 0. But it could be infinity as the running time if you run into an infinite loop. Space is a little more subtle maybe. There we say it's the size of the tape content that you ever can produce as an intermediate state. You start from the starting state, you somehow get to this position where you have alpha beta on the tape, and then you keep going until some halting state. And here I have to restrict that we don't have just a lot of blank symbols in there. The way we defined the relation might not be needed because we only move with the read-write head. So I think you could drop this. Either way, space is as much tape as you've used, right? It's intuitive too, I guess. And my point on this slide is I can, in one line each, rigorously define what time cost and space cost is for the model. That's why I went through all the pain of formalizing things. Once you've done that, you can be very clear about what these definitions mean without having to fluff it. There's these tricky cases for non-deterministic machines. We will soon get rid of those. But for now, they're included in the definitions because you can present me a completely useless machine, and the definitions are supposed to still make sense. Now we're coming back to TCS, theoretical computer science, where you would have spent a lot of time talking about languages, formal languages, which are just sets of strings. And we'll also use that in complexity theory. So I've talked about the function computed by a Turing machine. We can use that formalism to define the language accepted by a Turing machine. Formally, just say the language is a set of strings, so it has a characteristic function. It's a function that is 1 if the input is part of the language and is 0 otherwise. And so you can just have the machine compute that function. You give it a string and it either outputs 1, then it's part of the language, or it outputs 0, then it's not part of the language. Here's the formal definition. Again, for non-deterministic machines, they might output several different values. And so let me stress this here again. A word is part of the language accepted by a Turing machine if there is a way to produce the output 1, some way to produce the output 1. There might be many other computations in a non-deterministic machine that produce other outputs. In particular, some might say, no, it's not in the language, output 0. As long as there's one computation that produces a 1, it's part of the language. That is non-determinism in the way we use it. There might be many ways for the machine to branch out. As long as there's one that accepts the word in the end, we treat it as part of the language. Okay. A side remark on I think there's 2 slides on essentially, these are the general definitions, and you can produce many Turing machines that are annoying and don't make sense and are kind of broken. So we'll have 2 statements that say we can get rid of some of these awkward cases. One thing I'll just throw in, you can define a Turing machine that has several tapes instead of just one. And it can independently move a read-write head on each of those k tapes. K is a fixed constant, so maybe 5 tapes, okay? And then all the definitions have to be modified so that there's 5 positions at each point in time. You can do this, and it's sometimes more convenient to work on those machines if you describe a computation. If you have a single tape and you want to say, count something in one place and do work on some other place, you always have to walk back and forth. And that's a bit unrealistic that you can't access 2 pieces of information that are far apart. And so the K tapes allow to do that. But lo and behold, in terms of the running time, there's not a huge difference if you are on the polynomial versus super polynomial side of things. So if you have a K-tape Turing machine that accepts some language in a certain time, f of n, then you can also accept the language with a single tape, and you might square the running time. Squaring the running time in all practical terms is really bad, but as a theoretical construction, it's fine. It just means we don't have to bother with several tapes for the definitions of what a computation is, but we could use several tapes to describe a computation and then invoke this result to say there is a way to do it with 1 tape. It's just going to be more tedious and a bit slower. I wanted to throw in this vocabulary here that models are polynomially equivalent when they can do something like this, when one can simulate the other, where the time might blow up, but only by a polynomial amount. Okay, so far our Turing machines might do stupid things like run in infinite loops. And for talking about algorithms and running time, that's inconvenient. We'll want to speak about worst case running time. This makes it extra inconvenient if there's some computations that run forever. And luckily for all of the things that we do in this module, we can exclude all those cases where they run forever. So we'll leave the general case for undecidable languages and all this behind. The definition of what I mean by don't run in cycles is this. Turing machine is always terminating or computes a total function I'll try to use the always terminating. I find it a bit more intuitive. If there's a way to bound the time it takes, so there's some function t, so that whenever I have a computation from some initial input in the initial state, and I go through a sequence of computations, there has to be an upper bound on how many steps I can possibly go. It's basically ruling out infinite loops. That's all it does. But it also gives you a little more, because then we can speak about the running time, which is bounded by this function t. And that's a function of the size of the input, the number of symbols in the input. That's what we put into this function. So always terminating has these two sides. There should be an upper bound on how long any computation can run, but it also should be possible to reach the halting state. This part could be unfinished computations that somehow get stuck. This is only really possible for non-deterministic machines. Okay, for all those nice machines, always terminating, the time it takes to run on a specific input, remember that's the worst number of steps you could possibly take, will be at least 1. You never do nothing, and it will be at most this function of the input size. Okay. If you wonder, that's a definition, and I can wish for my machines to be like that. There's more. You can also make them be like that. And that's what this lemma gives you. It's if you're given an arbitrary Turing machine that might do all the stupid things I mentioned, in particular, it might run in infinite loops. And I give you some function with some mild side conditions. I'll comment on that in a second. The idea is that you want the machine to do at most t steps, t of the input size, and then stop for sure. And the lemma says we can basically make it so by counting up to this time steps and then stopping. The formal way to say this is we're given one Turing machine as input, and we produce a different machine as output, which is always terminating. And it simulates this original machine for exactly that many time steps at most, and produces the output that it would have produced on the other machine. But if that machine doesn't finish in that time, it produces a special timeout output. And you can also bound how long it takes for this machine M prime to do so. Again, we have this squaring of the time that we want. And I don't want to do a formal proof of this, but the idea of how to build this M prime is that M prime first computes this function of the input size. So that's where the mild side condition come into the game. There must be another Turing machine that computes this function t for us, and in a reasonable time. So I can certainly compute the length of the input and count that as a binary number. Then I can pass that to this other machine. I can simulate what this other machine would have done to compute t. And I can produce t as a unary number, so just as many little ticks on my tape as t of the size of x is long. And we can be creative. Let's put a little, this is a little watch, a little clock. So that's a symbol that I include in my alphabet. Why not? So this has to be part of my tape symbol for the machine M prime. Now the idea will be I'll produce as many time symbols as I'm allowed to spend time later on simulating the other machine. So I execute one step of the other machine by reproducing its transition function. And then I'll delete one of those clock symbols. And when I run out of clock symbols, I have to output timeout. If the computation of m stops before, then I also stop. Well, there must be a way to compute the function t. And in general, not all functions are computable, but if it's some polynomial, say n to the fifth, there's a program that produces n to the fifth many ticks on a tape by, for example, nesting 5 for loops within each other, right? For I from 1 to n, for I from 1 to n, 5 times. Pardon?
How do we know there's no clocks left?
Well, you can, it's a bit tedious to do it with the transition functions, but it's possible in general. You have a special state that says, now I'm scanning left. You have to say where the clocks go, either on the left end of the tape or the right end, whatever is more convenient. Doesn't make much difference. The time squaring comes from the fact that after each time step you simulate, you have to walk back to your clock symbols to remove one. And so the distance you have to walk is at most the space usage of your machine M. And the space usage is actually at most the time, because it just doesn't have more time to produce garbage. So there's a whole bunch of things I'm skipping here. That's the rough idea. Maybe you have yeah, let's leave it with a rough idea. I think the construction itself is not as important. The consequence for this part here is if we're only interested in the existence, is there some way to do it on a Turing machine with polynomial running time? Then we can restrict our attention to these always terminating ones. Okay. So again, fleshing out this construction in full detail would take a bit more time, and it's fun. There's one construction in the book where they specify a complete machine. I think this construction is not in that book. Once you've done a few of them, you get a feeling for what is easily doable, but it's tedious each time. It takes ages to spell out the details. Okay. So to sum up, Turing machines are a model where it's relatively easy in a few slides to rigorously define what computation is, what running time is, what space cost is, and all that. The downside is some ways that you can write down a Turing machine make no sense, so you want to restrict to something more sensible, at least these always terminating ones, by simply forbidding you as the programmer to produce Turing machines that make very little sense. But we have to make this as a second result. Just to make that point explicit as well, we talked about the cost to add 2 integers. And I said the ultimate answer is the word RAM model if you care about the precise number of, the precise time to add 2 numbers. If you stick with Turing machines, you're always going to end up with the logarithmic cost model. Or, so that's the way of saying the word size is constant and the input might be bigger. Because Turing machines have a finite alphabet. The tape symbol is finite, whereas word RAMs effectively have a logarithmically sized, well, now, their alphabet size is 2 to the W. For the kind of polynomial, non-polynomial doesn't make a difference. Specific questions about the Turing machine? There were questions on Slido. maybe you have to remind me what exponentiation there was. I'm trying to think of where it was.
A number of
Oh, it's power set. Yeah. Sorry. Okay. Let's still go there because that's important. This part here. So 2 to a set, that's the set of all subsets of S.
excuse me, we cannot see.
Yeah, I have to switch back, sorry. So this is one way to write this. Sometimes people write calligraphic P of S, or I don't know. I think I've seen this, but that's a bad choice, I think. It's just the set of all subsets, power set. Yeah, sorry about that. Good point. And okay, obviously someone learned their lesson from efficient algorithms. The Knuth-Morris-Pratt string matching algorithm, that is, it has these notions of failure links. That's much closer to a finite automaton. So it's in a way you can see it as a restricted subset of Turing machines. The thing about Turing machines is that they are way more general, more powerful. It doesn't look like it when you see them first time, but they can do a lot of simulations. Okay, let me come back to this last point. While this was lovely, we will not always want to go to the full formal level of specifying computations. I think it's important to have it as a background to be able to go back to this if you're unclear what something means. This will happen. You have some statement and it's not quite clear how to decipher it. Then you want to be able to go to a formal level so that you can answer the question. But for working with things, you often get away with working on a higher level of abstraction. And that's what we'll do in the following, where we'll just say algorithm when really we should say a Turing machine or even a deterministic Turing machine. The reason why I use algorithm is it's a bit more intuitive, and you could in principle replace a Turing machine with one of the other formalisms and it wouldn't really invalidate the theory. With that prep, we're now able to define formally what we had initially as just a rough idea, these classes P and NP. So here again, essentially the same definition that we've seen on Turing machines on the more high-level construction of an algorithm. Here we have a different input and output alphabet. I don't remember if there's any case where we really need that. There's a total mapping that this function, that this algorithm computes. It takes a string from this input alphabet and produces a string over the output alphabet. It's really the same like in the Turing machine case, right? We had a specific string that we start with, blah, 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 go through the computation, reach a halting state, and then we've produced the output. Same thing. And then we denote by time, small case time of x, the time and small case space is the time complexity or space complexity that the algorithm has on this input. And this is not very rigorous, right? This is just saying there's something like time complexity, but you can do the formalization over Turing machines, or you can get away with a more abstract cost measure for most cases. So nothing new, and we could always go back to the details. The new bit is we need a way to go from the time or space of an instance of a specific word or input x to something talking about the size of inputs, which is where all the analysis of algorithms really gets started. So the same setup, and now the capital case time and space take not the input, but a size as input, and then it outputs the worst case running time. Okay. The largest time it ever takes for a string of size n, So x is a string, so we can say how many letters it has. That's the input size. And space is totally analogous, same thing. Okay, so that's just the notion that we treat all strings of the same length as one type of input, and we take the maximum over the time there. So far, we've mostly talked about functions that are computed. Now let's get back to algorithmic problems. And I alluded to this in the beginning. We'll focus on decision problems, which are formally a language. Informally, you're given an input and you're just asking a yes-no question. And the yes instances are elements that are in the language. The no instances are elements not in the language. And an algorithm is supposed to solve this problem by either outputting a 1 or outputting a 0. If x is in the language, should output 1, otherwise 0. That's the characteristic function that we've seen before. I think this is all the same. The only new bit would be the notation. This calligraphic L of an algorithm, again, is this set L, this language that's accepted by outputting a 1 if you give it the element as input that's in the language. So again, decision problems, you're given some input and you ask, is it in the language? That's a yes-no question. If you find that hard to relate to typical algorithmic problems, here's an example how it's used. It could be the traveling salesperson problem. So the input there was this distance matrix and a threshold. To turn it into a yes-no question, you have to give it a bound on the tour length. And then the question becomes, is there a way to go through all the cities in this distance, with this distance matrix, so that the total length is at most d? Then the language would be some way to specify that. So you would somehow have to encode the graph in a string and this number in a string, combine the two things, and that's your language. Because our Turing machines, poor things, they can only work with strings. But I guess if the web has proven anything, that everything's a string, so it's not a restriction. Okay, if we have an algorithmic problem, we could define an upper and a lower bound for the running time. In essentially the obvious way, we say an upper bound is a running time function is an upper bound for this problem if there is an algorithm that solves this problem in that time. And a lower bound for the problem is another function where we can somehow prove that every possible algorithm needs at least that much time. That's just coining these two terms because they're used in algorithmic literature a lot. And people also use optimal, although I'm not a fan of this because it's so unspecific. Optimal just means an algorithm that is in the same theta class as some known lower bound. So you cannot improve the time of this algorithm for that problem by more than a constant factor. That's what people in algorithm theory often mean when they say an optimal algorithm, which is a bit unfortunate because this optimal is only optimal if you ignore constant factors for large enough inputs and in the worst case. Okay. We still haven't made it to P and NP, right? There's one step missing. We define classes of problems now. That's the capital time, all cap time, given some running time functions. So you bound now how much the problem is allowed to scale up in complexity given an input size. And then time of this function is the set of all languages or algorithmic problems for which we can find a Turing machine that accepts this language and uses at most f of the input size as its running time. So here that's true for all. So again, it's a kind of a worst case notion because it has to be true for all possible languages and all possible words in the language. And based on that, we can define the class P, which is the union of all these time classes for all polynomials. So all polynomial functions is effectively, you could have written this as the union over all constants C, and then it's time of n to the C. It's a bit more convenient sometimes to write it like this. But effectively, there must be an upper bound on the running time of the form n to a constant. N to 1,000 is fine. Any constant C is fine, but it has to be a constant, not grow with n. And any language in this class, so any language for which we can find a Turing machine that accepts it in time bounded by some polynomial, we call that a tractable or efficiently decidable or efficiently computable class or language. That was P. So far, so good. I know the pace today is a bit rough. I want to cover as much ground so that you can do the mini seminar well. And at the same time, for 3/4, it should be a repetition for you. I just don't know if you have done it with the same formalism at the same level of detail. So I thought the best compromise is to run through it quickly and show everything, but not spend a ton of time and give you a fair chance of digesting it if you see it for the first time. But the video is there for you to rewatch, and there's the books. To define this other class, NP, we need to come back to non-determinism. And this is just a recollection of what we've just covered, so maybe it's not so far away. A non-deterministic Turing machine accepts some language if there's some way of a computation that outputs 1 that accepts this input. But if a string is not in the language, then every possible computation has to reject it. That's the flip side. So there's an asymmetry, right? It's easier to accept something in a way than to reject. If you reject, then you have to reject it in all possible computations. We restrict our attention to these always terminating Turing machines. Don't do infinite loops. Everything has to have an end. And yeah, we define the time to be the longest possible computation if it's a non-deterministic machine. I've said that in detail before, but just to recap, yeah. Does that imply what?
Like in the difference of cost for because we could just use the longest computations, but just split the computations into shorter ones and
well, non-determinism it still has a well-defined length. It's not like parallelism that you can branch off and then come back at the end in some way. Right? Non-determinism just says there's different options. Universe, let me know which one to pick. I don't know. All of them are available, and there's no effective way to know which one to take. Maybe it'll become clear in a second when we have the other formalism for this. Keep it in mind. We have a similar notion to time, which is n time. That's same setup. We have a bound for the running time. Now it's a set of all languages for which there is a non-deterministic Turing machine that accepts it in that time. Otherwise, the same thing as time, but n time means non-deterministic. And then the class NP is defined analogously to P. Again, the union over all polynomials, but then using n time. And that sounds like not such a big deal in the definition. It's very similar, right? Should be that the problems are also similar, but of course you already know that that's not the case. Maybe you deserve a few minutes break. Let's continue at 1:15. And I'll check how fast I have to go. Ja.
Das würde ja eigentlich heißen, bei einer nicht-deterministischen Verschwörung könnte es jetzt vor allem ich denke jetzt nicht Spitzen sein, wenn ich dann in der Zeit knapp baue. Mit einer nicht-deterministischen Maschine.
Wenn Sie eine bauen könnten, schon, ja.
Ja, schon, aber halt in den theoretischen Modellen. Das
Ja.
ist eine lineare Laufzeit.
Ja, genau. Man kann damit exponentiell viele Sachen ausprobieren in linearer Zeit. Weshalb auch, das Modell ist halt Quatsch, ja, das ist unrealistisch. Man kann die nicht bauen.
Ja.
Aber das ist mit Absicht so, sozusagen.
Also theoretisch könnte man das aber beschreiben als eine Maschine mit Querelen.
Man müsste halt, also ich denke,
Oder
es
man
ist,
könnte die davon überzeugen, mit mehreren Kernen zu arbeiten.
aber jede Maschine, die man baut, die mehrere Kerne hat, hat ja trotzdem eine feste Anzahl Kerne.
Eben, aber
Und
halt
diese,
viele Kerne. Das ist ja das.
ja, exponentiell viele in der Eingabegröße. Schwierig, oder? Also in jedem Zeitschritt, mindestens könnte man in jedem Zeitschritt 2 neue Zweige aufmachen.
Ja, okay, aber das ist ja auch.
Und das heißt, nach n Schritten. Bitte?
Ist ja trotzdem nicht.
Ja, es ist halt komplett übermächtig. Nicht deterministisch ist zu mächtig, als dass man es realisieren kann. Es gibt nichts, was irgendwie exponentiell in der Eingabegröße wachsen könnte für länger als ein paar Schritte. Und insofern, ja, also das ist oft so ein Ding, wenn man Nicht-Determinismus versucht, intuitiv zu erklären, dann ist es ein bisschen wie Parallelität. In gewissem Sinn schon. Ja? Also es laufen mehrere Sachen und es reicht, wenn eine davon erfolgreich ist. Man könnte so einen parallelen Algorithmus schreiben, der sagt, ich führe mal verschiedene Algorithmen aus und wer als erstes fertig ist, schreit hier und alle anderen hören dann auf. Das kann man bauen. Aber was man nicht bauen kann, ist ein exponentiell paralleler Algorithmus. Das hilft nicht. So viele Kerne haben wir nie.
Den Algorithmus könnte man ja schon.
Bitte?
Den Algorithmus könnte man ja schon.
Könnte man hinschreiben, aber er hätte exponentielle Work. Und wie wir dann ja wissen, ne, ich muss Work durch die Anzahl Prozessoren teilen, wenn ich Wall Clock Time kriegen will. Und wenn das nicht auch exponentiell ist, dann gewinne ich nicht viel.
Ja, okay. Ich weiß nicht, ob ich nicht einfach mal arbeiten.
Haben Sie ja was Neues erfahren zu Vorlesungen einbringen?
Ich habe gefragt, dass das Prüfungsbüro eine Viertelstunde zugemacht hat, bevor ich da gewesen bin. Und ich werde den Mail schreiben. Weil
Okay.
die Zeiten sind zumindest eigentlich gepasst.
Ja.
Ich habe noch nichts.
You're very disciplined. It flipped from 14 to 15 past, and the room went silent. Was that coincidence? Let's take it as a good sign, and we'll see next time how it continues. But let's continue. In the next section, we'll look at a different way to define NP, which is equivalent. It's a different characterization but which is a lot more intuitive to work with. During the break, we had a quick discussion about non-determinism and how it is similar and maybe not similar to parallel algorithms. The main point, I think, is worth mentioning for everyone. A non-deterministic machine can essentially spawn an exponential number of threads and not pay anything for it. And that's unrealistic. So just to reiterate, you cannot build a non-deterministic machine that simulates these problems in NP in any sensible way, in any efficient way. The point of this definition is a different one. It's sketching out what would be possible with these machines, but they're unrealistic. A different way to look at those is via verifiers, also called sometimes certificates. And so the idea is as follows. We can define a different notion of accepting a language. It's a bit awkward at first, but you'll see it maps very naturally to typical problems like the traveling salesperson problem. We have a language again, and now an algorithm is given a word of the language, but also some other thing, namely a certificate, which here will just have some binary string. So the input to the algorithm is a pair, a potential word from the language, where we have to decide, is it part of the language, yes or no, and some mysterious binary string. Now, such an algorithm is a verifier for this language if the following holds. For every the language is exactly the set of all strings, so that there is some binary string C, a certificate, so that the algorithm outputs 1 if given W and C. Okay? And then we say that this binary string C is a proof for the fact that W is in the language. And that's precisely, I think that the term is intuitive and telling there. Let's do an example first. So if L is the traveling salesperson problem, so a yes instance is a distance matrix and a threshold, so that the shortest Tor with those distances actually has a length less than the threshold. Okay? That would be the language L. What could be a certificate? Well, the round trip itself. So somehow encoded in binary, but if you give me an instance of the traveling salesperson problem, a graph encoded, or the distance is encoded, and the threshold, and you also present me a Tor, I can check if that Tor has total length less than the threshold. And if I find such a proof, such a certificate, I can easily verify in polynomial time as well that such an instance is part of the language TSP. On the other hand, if you give me an instance where the shortest round trip is longer, I might have a very hard time to find any proof because there is none. And this is where the definition says nothing about it. Okay, I was jumping ahead of myself with this polynomial time verifier. This is just saying an algorithm is a verifier if it somehow solves this definition. So it accepts a word with a proof if that indeed is in the language. And a verifier is an algorithm, so it has some running time. If that time to accept a word is polynomial now just in the length of the word, the certificate is excluded. Which also means that the certificate had better not be too long. Otherwise, no algorithm has the time to even read it. So that naturally bounds, without explicitly mentioning it, the certificate cannot be substantially longer than the input string. Otherwise, it wouldn't be a useful one. Proofs need to be readable. Then we can define the class of problems, VP, those that can be efficiently verified by, well, all the languages for which there is a polynomial time verifier A that accepts exactly this language. Okay? And again, the example was L could be TSP yes instances. which was the distance matrix and the threshold. I think that was the notation I used on some slide initially. But you know what I mean. That's the distance matrix. You just write down all the numbers. You give it a threshold, all the numbers. And the yes instance means there is a round trip that has at most distance capital D. Let's spend a minute comparing these two things. After the proof, I think it will not be surprising, but maybe at first sight it is. These two classes are the same. NP and VP describe the same problems, which means we can either think about non-determinism or we can think about verifiers. It's the same thing. This is a statement about a set equality, so we prove it by both inclusions. And the first one is we show that NP, is a subset of VP, which means I'm going to pick some arbitrary language L in NP. And we'll eventually want to show that this language is also in VP. Right? If it's in LP, that means there is a non-deterministic Turing machine A. Let's call it M like before, so that L is the language that's accepted by this non-deterministic Turing machine. And it's also polynomial time. I'll just write briefly polytime to mean that what would be properly right? The time it takes machine M on an input of size n is big O of some c, and there exists a constant c such that that is true. Okay. Now, with this machine M, we're going to construct a verifier for the same language. And so that one's supposed to get an input from the alphabet. Let's say L is a subset of some sigma star. And this verifier is supposed to take some word of sigma star and some binary string. So let's take this sigma star and 0, 1 star. The core idea of the simulation is M is a non-deterministic machine, so we only know if X is in the language that there's some accepting computation in M, but it has these non-deterministic steps where we don't know which step to take. In each possible case, so at each point in time, M has only a constant number of possible things to do because all its control is finite. If you go back, the delta of some state and the current tape symbol, I don't know, let's call it A, it has that many different options, and that's less than some constant C. So we will use some log C rounded up. I'm just saying we use the binary bits in C to pick one of the possible outcomes one of the possible next steps in the non-deterministic computation. So in a way, we use C as if some all-knowing person had written down exactly which are the right steps to take so that they lead us to the accepting computation. Now, in general, we don't know which the accepting computation is, but the good thing is the verifier also doesn't need to know. It gets the string C as an input, and it's supposed to accept if there's some certificate. It doesn't need to know which one it is or find it. Okay. And that's basically all we do. So if M accepts a certain input, then that's happening if and only if there is some accepting computation we could even formally write down what that computation looks like, right? It starts from a starting state and then it goes with a number of steps to some halting state and 1, but we don't need that here. So that it accepts the input X. And that means there was a selection of possible next steps at each non-deterministic time step. A. Okay. So we simulate the non-determinism by writing down the choices. And if M accepts the string S, if and only if there exists a C, so that A accepts XC, that means the language accepted by the verifier A is our language L, and that means L is part of VP. And that's the end of this first bit. It shows every language in NP is also in VP, so that's the inclusion part 1. Now let's do the other direction. We also want to show that VP is a subset of NP, but the idea is very similar. So we have an arbitrary language. So we start with a verifier for L, arbitrary language in VP. And we construct the non-deterministic Turing machine. Let's give this a name. There's also polytime. I can do this properly. So there's a polytime verifier for A. We construct a non-deterministic polytime Turing machine for this language, where we use the non-determinism to guess the certificate. That's called non-deterministically. What that means is it's a binary string. So I'm going to do a number of steps where in each point I can do one of two outcomes, and one writes a 0, one writes a 1 into my string C. And I'm doing this non-deterministically, which means someone has to figure out the right path. I'm not going to do it. I'm non-deterministic. But that way I can effectively try all possible strings C. But it's non-deterministic, so I'm not even paying for it. And then for the rest, I'm just simulating A. And this part will be deterministic. I don't need to do any further guessing steps there. And you can work out the same. The running time stays the same. You don't know how long the string C in general has to be, but we can bound it by how much time A has. So you don't have to generate an arbitrarily long string, or you could even interleave the things and be smart, so you only generate the next bit of the string C when A in its computation accesses it. Before you read that bit, it isn't relevant, so you could also delay the guess it on demand, basically. But the same thing as above here is true. If there's a way to make the verifier accept, if there is a proof, then there is a way that the non-deterministic machine uses the right steps to guess that string, and then it simulates it so it accepts the same strings. So that language is in NP, and that concludes the proof, because then every language in VP is also in NP. We should already know every language in NP is already in VP, so the two are the same. Okay. This is useful whenever you want to show that some problem is in NP, because again, if you were to apply this to, say, the traveling salesperson problem, you can show that it's in NP by showing it is in VP. As I sketched before, if you give me a distance matrix and a threshold and a round trip, it's really easy to just sum up the costs of the round trip and check if it's smaller than D. That's just linear time or so. Okay. Last little bit is getting into reductions and hardness. That's actually a quick part from here. I'll skip some intermediate parts where the proofs are on the slides and we don't necessarily need them. I'd rather show you one of the reductions, which is what you're supposed to do in the mini seminar then. In the next section, we'll look at reductions from one problem to another, and then finally get to this notion of NP completeness. Again, recall we're looking at decision problems only. It's all about languages and machines that accept them. We've seen that example before. And we'll speak, in terms of problems, we'll speak of things that are in the language as of yes instances, where the answer is yes and otherwise no. In the TSP example, a yes instance is one where there is a TOR that's less than capital D. A nitpick that I mentioned for TSP but didn't go into detail is if we encode everything as a language, everything has to be a string. As I said before, computer science is all about turning things into binary strings, so that maybe isn't so surprising. But whenever we have a problem that's defined on more abstract constructions like a graph or whatever else you can come up with, combinatorial structures, you need to encode it as a string. But it's often enough to just use the standard data structures you learned in undergrad data structures courses to represent things in a computer. It's the same problem. You also have to represent a graph in computer memory. That's effectively turning it into a string. So the same trick usually applies. The thing to stress here is that n, the input size we've always talked about, really is the size of this encoding. So you have to be a little careful that the encoding is not completely nonsensical. If your encoding for the graph would be very wasteful, then you artificially blow up the input size. And that might give you strange results then for the running times. That's just a little caveat. What we'll come to now is this picture comparing nuts by hardness that we've seen before. And the key definition for this is the notion of a carp reduction or a polynomial time reduction or polytime reduction. There's less or equal p, where p stands for polynomial time. So we have two languages, a language A and a language B, as up here. And we say that A is polynomial time reducible to B. Bit of a mouthful, that's why the abbreviation is often used. If there is a function that maps from the one language to the other language, or from the superset, from the alphabet of the two languages. It must be computable in Poley time, so we have an algorithm that computes this function g. And now the crucial property is this. For all words in the original, in this sigma star, we have the word is in the language A if and only if the outcome of this reduction is in the language B. And it's important that the implication goes in both ways, right? A word in A has to be, if W is in A, G of W has to be in B, and vice versa. For every word not in A, G of W may not be in B. If you compare this with the intuitive notion, we're actually asking for something slightly stricter. For this implication that any algorithm for B implies an algorithm for A, you could have allowed, for example, using an algorithm for B as a subroutine and call it several times. This we're not allowed to do here. We have to take the input, transform the input to a different input, and then apply once the algorithm on the other problem, and that's it. Also, the output has to be the same. I cannot flip between 1 and 0, yes and no. That's what carp reductions do, and that gives some nice properties that go beyond this intuition. The results I'm not going to prove is this. If A reduces to B and B is in P, then A is in P, and the same holds true for NP. These are all simple proofs. What it comes down to is that right, we need that definition though. We've defined a reduction. Now we need to define NP hardness and NP completeness. That we haven't done yet. But it's a simple definition based on these reductions. A language is called NP hard if every language in NP reduces to A. And that's a mouthful because you would have to somehow show that for every possible language in NP. And NP complete is the same, plus we require that A is in NP itself. Whereas NP hard could also mean A is much, much harder than NP itself. There are things outside of NP. We won't talk a lot about them, or at least not now. But there they are. And so NP hard just means everything reduces to A. NP complete means A itself is in NP as well. And that's the key result, that the intuition with the I can find a solution, but neither can all these famous people that relies on. If I have an NP complete language, any single problem, TSP, then this problem is in P, has a polytime algorithm, if and only if the whole two classes are equal. All of the other problems also have a polynomial time algorithm. And because we believe that that's not the case, we shouldn't expect for an NP complete problem to find an efficient solution. Again, I'm going to skip this proof. It's not hard to do. And instead, I want to show briefly an example of a reduction. So looks like NP completeness tells us a lot. Do these problems even exist? It turns out that this is a transitive reduction. You can reduce all the problems to some problem A, known to be NP hard, and then do a single reduction that you have to prove. That's what you're going to do. And then you inherit that all these problems via A should reduce to B. As long as we can find a single first NP hard problem, all further proofs of NP hardness can do a single reduction. That's what this slide says. Okay, let's skip that. The Cook-Levin theorem was the result that there is a first NP hard problem, namely the Boolean satisfiability problem. You'll have to look at the definition if you don't know it. I'll skip over that for now. And the proof here uses that you can use a Boolean formula to simulate the computation of a Turing machine. Again, we don't have time to dig into this in detail. If you want to read it in full detail in slightly different languages in the book. For those of you who can read German, I wrote an algorithms book that also has the proof spelled out, but it's in German. Let's try to squeeze one reduction into the last few minutes, okay? It's spelled out in detail on the slides, but let me give you the gist of it. A more typical example of a reduction, the one that we'll look at, relates this problem 3SAT, which is a Boolean formula where everything looks like this. It's a big and what is in the AND parts is an OR of variables or negated variables. So all the inputs look like this, plus each of these clauses have at most 3 literals in them. So literal is this thing, a variable or the negation of a variable, and a clause is the OR of 3 such things, of 3 literals. And you can show that this is NP complete. Some of you will look at that. And the second problem that we reduce to is vertex cover. That's what I asked about initially. Vertex cover, on the example, you're given a graph and you try to select some vertices so that all the edges in the graph have one endpoint selected. So you could always pick all the vertices and satisfy this, but the goal is to find a small subset of the vertices. And the decision version has a threshold, so you're not allowed to pick more than k vertices, and you want to satisfy the condition that every edge has one endpoint selected. For example, here, a smallest vertex cover uses 3 vertices. Then all these edges have at least one endpoint selected. It's fine to have both endpoints selected. And you cannot do it with just 2 vertices, in this case by just trying all options. And the full proof should show that vertex cover is NP complete. That consists of 2 parts, showing that it is in NP and that it is NP hard. And let's only sketch the NP hard part. The intuition that you should follow, and that's what you do in your reductions too, you take the new problem, vertex cover, and suppose that that is solvable. And now you take an instance of the old problem that's known to be NP hard, and you cast it in the language of this new problem. So we express a 3SAT instance, a formula, as a graph, so that the vertex cover of this graph says something about whether or not this formula can be satisfied. Okay, and here's the formal construction. I only have time for the example. Here's a formula. It has these clauses. For each clause, you make a little triangle, and it's connected by these blue edges. And the vertices are labeled by the literals in the clause. That by itself wouldn't be interesting, but you add green edges between every 2 literals in different clauses that contradict each other. So here I have x1 and not x1. I cannot have both at the same time, put an edge between them. And you do this for all pairs of literals. If they are a variable and the negation of the same variable, put an edge between them in green. And then the key observation is that if that formula is satisfiable, it means there's a way to set the variables so that in each of those cases, one of the 3 at least is true. And then you can pick the true thing and make that not part of the vertex cover, but take all the other vertices. So here you would read off an assignment of the variables that satisfies the formula by setting x1 to false, x3 to false, x1 to false again, okay, and x4 to true, and that should satisfy this formula. Now the thing is, if there's a way to pick from each triangle 2 vertices such that all the green edges are covered, then you exactly satisfy the formula, and that's an if and only if. It goes both ways. The full proof in all details is spelled out on the slides. So if you haven't seen this example before, you can read it there. I hope it's actually clear enough even without my voiceover. That's a classic example that you may have seen elsewhere, and there's many explanations out there too, but it's not one of the ones in Karp's original paper. So I wanted to present one that you're not going to work on. Okay, that bit admittedly was too quick to properly follow, and we didn't do the full proof, but I'll put the slides online. I'll also be in touch with more precise instructions what the mini seminar looks like, including deadlines and what you have to deliver. So just watch your emails, and please sign up on Campus Wire so that we have that platform as well to communicate.